Yeah.
And that will be till your 30 minutes, right? So if you want 10 minutes per question or 5, you can do them.
Yeah, I planned it to be like 20 minutes, so I stop
Okay.
at here.
Oh.
Yeah, that's definitely. Yeah, also don't have notes on the slides. I get every time surprised.
Yes.
With
Yeah,
notes.
yeah. It's just like too much to see.
And then it'd be like. It's expansion on a more higher level, namely on those syntax nodes, which you can see here. So here on the right, you have a representation of our macro body as this syntax tree, which then gets expanded into the language. The advantage here is that with lexical macros, you could introduce errors, syntactical errors, while with the syntax macros, you can ensure that you do not introduce syntactical errors. We will be focusing on the pattern-based and the syntactical macros. So let's dive into the architectural description languages. Well, the big domain is, of course, the domain-specific languages. So it's a subgroup of this domain-specific language group. And they are used to describe something, describe a system. And that's very important. We do not want to execute anything. It should purely be a language where it describes something. And this is also why we did not want to use the procedural approach, but the pattern-based approach. Why you need this? Well, you can generate certain artifacts with it and verify those artifacts. And then there is this distinction between implementing it as part of a host language or have it as a standalone language. For our Vienna architecture description language, we chose the standalone approach, and it is a processor description language. So this is even a smaller part of the ADL family. So it is used to describe a processor. It is work in progress, and why did I highlight it? Well, it's very nice to have this macro system to test out different features we would like to have for our main language. So here, these two parts can play very well together and drive each other. Here you have a quick overview. So left-hand side, you have the specifications, which go into our tool. The specifications are written in VADL, so we call the tool and the language the same name. And on the right, you have the generated artifacts. We will be focusing on the instruction set architecture specification in VADL, and also designed the macro system around it. So how does this look? In the instruction set architecture, we want to define the behavior of such instructions. So let's start with a simple add instruction. We have this keyword instruction with an identifier add. Then we have some type information. Don't worry about this now or ever in this talk. Then we have this behavior body where we have this addition and assign it to the third operand. So what's interesting here is just these parts. Keyword, we have a name, and we have this plus operation from two operands assigning to a third one. Then to have it for to generate an assembler, you need also the assembler, of course. So you specify it in form of this string concatenations and encoding, where you specify the bytes in which you encode it. But this is just to give you an overview on how much code can accumulate just for a simple instruction. And as you can see here, this is just for an add instruction. So what about other binary operator instructions like sub, and or? You would have to repeat this whole process for every one of them. And this is something we do not desire. We do not want to repeat ourselves. So this is where the macro system comes into place. First, we take our instruction. From now on, we will just focus on the instruction behavior to make it much simpler. We take the interesting parts. For us, it's just the name and the operator. We replace it by a placeholder. And now we have our template body. And to use it, and also use it in a type-safe, a syntactically type-safe environment, we wrap it around something which we called a model. So a model for us is this typed template that contains these pattern bodies which have these placeholders. So you can already see here, we use this dollar for switching the context between a language element and a macro element. So let's go quickly over the model. We have the name, the binary instruction, which is the name of the model. Then we have a typed parameter list with ID of the type ID and op of the type bin op, and we get an ISA definition as return type. So these blue types here are syntax types. So those are just types in the realm of macros. So they are just types for the nodes that we parse. They're not in the language per se. So Now that we have defined it, how do we use it? Well, we simply call it with this $sign and give it the respective name and the operand. So here, this is how we would use this model and define the add, sub, and or. So far, so good, but what about more complex instructions? So in architectures like ARM, instructions can be predicated. So there is this if statement here that would only execute the instruction behavior if the condition is true. Here it would be that it checks a condition flag. This could be a compare before this instruction. And in our case, it only executes if the compare before this instruction was equal. This brings us, so these are the interesting parts now. And this brings us to the problem that for the ARC32, we have 15 different of these condition flags. So let's try to pack this into our macro system. If we try it with a very naive approach and simply extend our binary instruction, we derive something like this. So extend ID here is a lexical extension we added so that we can have this, so we can generate new IDs in a way that we can control the ID name. So here it would simply do a string concatenation and return an ID in the syntactical manner in a very safe way. So we extended our model with a condition and a postfix. As you can see, there are just IDs and a string. Now, when we start now specifying each instruction, we quickly realize, okay, this cannot be the way. This is too much code we write here. We write 15 times each binary instruction we have. So what we came up with as solution to our system is this higher order macro concept. So first, we take a look at what we already have. So we have this very generic version of our binary instruction template, which we like a lot, but it can be improved. So first, we separate the concerns. So we generate our type composition or these record types where we have like one for the instruction information with the field ID and operand, and one for the condition information with ID and the postfix. Now we can use this, the names as types in our model. How do we use them inside of the body? Well, they're simply accessed as any record. So you have like the name, dot, and then you access the field. How do we give it to the model now? Well, we simply put it inside of parameters and the magic happens itself. So it has to be in that specific order as we defined the names, but this is how it would be done. And now we have it in a more abstract way, but we still have this, we still have to write a lot. So our idea is now to only once specify the different conditions and give this wrapper that specifies these conditions our binary instruction as argument. So first we have to kind of, or first we want to abstract a little bit the type of our binary instruction model, which is here represented with this inst type. So this is now a function type taking an inst info and a cont info and produces an ISA definition. So the inst type would represent the model binary instruction in the type sense. And now to the wrapper. The wrapper, and this is now the higher order, what we call it for the macro, can take now any model of this particular inst type as argument, which we can see here as inst type, and can then use it inside of its body. And now this is now comes the advantage here. So with this wrapper, we can now have this instant model called 15 times with our specific conditions on the right. So we pass it an information, this gets just passed through, and we generate it only, like we write only once the 15 conditions, and those get passed to every model we call our condition wrapper. Now, how can you call it? Well, you have this model binary instruction we defined before, you have our condition wrapper, and now you just call the condition wrapper and give it the binary model as argument, and then you give it the specific instruction informations. And as you can see now, we arrived at the same amount of code, but encoded a lot more of complexity as before. And what's here also interesting to notice, this approach, just for binary instruction, you could simply call it inside of the template, just with binary instruction. But with this approach, you can give it any model with this type. So you just define this condition wrapper once, and then you can give it not only binary instruction. For example, if you have a different behavior for shifts, or if you have a unary instruction that has like the similar setup with operator and ID, you can put it in here, and the wrapper will call the underlying instruction with the correct arguments. Now for the evaluation. We implemented this in our tool and tested it with our instruction set architecture specification, or more specifications. So those are the fours listed here. And we were interested in runtime and code size. So first, we simply took the number of lines. So in green, you see a program that has these macros in it. And in blue, you see a program where these macros got expanded and then printed again. So blue is without macros, green is with macros. The Y scale is logarithmic, so this is even more impressive. And you can see for the arc32 and arc64, we have like a lot of improvement here. For MIPS and RISC-V, this is slightly less, and as you can see here, especially for RISC, somehow we end up with more code when we have macros and less code in the expanded way, but this has a reason. And the reason for it is that the number of lines is a very bad metric for defining the usefulness. So we came up with we used a new metric in the paper, which basically just takes the syntax nodes, and now we can see that indeed for RISC, these very long one-liners now take no part anymore, and we just use the syntax nodes, and we can see that we actually have like less code to write than it is produced. Something interesting maybe is the runtime here, and while for MIPS and RISC, the runtime is very similar to each other. So we have in green the parsing, in orange we have a macro expansion, and in blue we have the parsing again with the expanded version of our program. So there are no macros here, it would be the long program. And here you can see for MIPS and RISC it doesn't really matter, but for arc64 and arc32 it matters, because in arc32 it was actually faster to have macros and expand it in memory than parsing the huge file that is generated by the macro. And for arc64, even though the runtime would be the same for the expansion, the parsing runtime is not the same. And since we use this syntactically typed macros, every second we save in parsing time, we get a faster IDE feedback. So this can improve like the IDE performance. Okay, so what are the final takeaways here? Well, a macro system, especially the syntactically pattern-based macro system, is great for specification languages. They make it much, it can be faster when the things you want to describe are complex enough, so to say, and it makes it definitely more concise. In this talk, I showed you this model element we had, which is this syntax type saved higher order macro template, and I showed you the record and the model type, which is basically the composition, like syntax types composition and the type alias. Thank you very much.
Thank you. You have questions?
Thank you. I'm Eric Heide from the University of Utah. Thank you for your talk. It's very interesting. So I don't know your domain very well, but my belief is that CPUs often have quirks and irregularities. Like for instance, some some instructions might not be available in all of their predicated variants for various architectural reasons, right? So there are 15 flags, but some instructions might be predicated on all, there might be predicated variants of all of them for some flags, but some might only be available, say only 5 of them are actually implemented on the core. And I guess, so first, my question is do you encounter that problem? Is that an actual problem? And second, do you have a way in your macro system to deal with that sort of thing easily?
Yes, very good questions. So the first thing is, yes, like we encountered where the semantics differ a little. For example, for shifts, we had this this challenge where it's some architectures required the shifts to be like casted to a certain value before having it as the operator, and there are similar approaches how we handled this. For example, you could just make a separate, very generic version of your shift family of instructions, and then you can simply put it in there and it does it magic. Or you can, for example, model this cast as an expression which you provide as parameter, and you can then, with like some clever ways, you could then only have it be used for a specific family of instructions. Yeah, so the second question, I think it was already a little bit answered right now with how we would deal with it. We have more in our language, which I did not present yet now, which is basically we have some kind of conditions. So we have like a pattern matching for different syntax nodes. So if a node is, for example, if you provide an ID, then we can pattern match on that ID, and if that ID has a certain name, for example, then shift, we apply other behavior than for others.
I had one more question. I didn't see a hand up. Oh, there's the hand. Your actual macros are, maybe they have a little bit more parameters than what you showed on the slide. So in particular, you had a semantic function, you had an assembler syntax, you had a binary encoding. Maybe there was a fourth thing. I mean, so presumably you would have to specify all of these things as parameters to your models, right?
Yeah. So basically, this is why we had it before without this composition, so without these records, and it was like huge. The parameter list was too much to be efficiently debugged. So then we introduced these record types to get a hold of this. And now with these record types, we have the separation of concerns. So now when we define something new for conditions, we simply have to look at this record for the conditions. Yeah, but yeah, we encountered this. It was, before it was a lot to read.
Hi, I'm Sulu from University of Zurich. Very interesting talk. So given the heterogeneity of hardware, right? So I understand this is about specification, right? But do you kind of imagine you can, because a lot of, say, compiler optimizations, right? They are kind of, so regardless of whether you can have like specific implementation details regarding, say, add or vector, certain vector instructions, right? But there are certain common compiler optimizations that can be applied to such, say, vectorized computations, regardless of the actual implementation, like the architecture details, right? Do you imagine this language, like this kind of specification, can also be combined with certain computations, like you can actually push that into certain compiler pipeline to enable some generalized optimization so that you can perform certain generalized optimization in an architecture-independent manner?
Okay, so if I've understood this question now correctly, it was okay, so this talk was more about this macro system, but I think the question you gave is more about the specification language, right?
Right, so like whether you can, I guess my question is, because right now, like the compiler is really kind of, it's architecture dependent, right? So you have some say you are optimized for this Intel version of GCC, or you're optimized for the RISC-V, right? And then, but there are certain overlapping at certain abstraction level. So for example, in your case, is this at the specification level, right? So do you kind of see there are certain ways you can bridge the gap?
Yeah, so there's, so specifically for the macro system, it would be then that you can, like you can also give it flags via the command line. And then, for example, you can say, okay, generate me now a specification that is specialized for the GCC compiler, or generate me a specification that is specialized for CLang, or just a specification which is used, for example, for this optimization steps. But in our case, it's more on seeing where the macro system can guide our language. So when we see, okay, we use this a lot and it makes sense to implement it in our language, then it would, for example, your question would be, I think, better solved in our actual architecture description language than in doing it with macros. So then you have like different entries in our language where it's handled there, yeah.
So in the title, you mentioned the macro thing being LL regular, and that just didn't seem to factor into the rest of the talk very much. So I was wondering if you wanted to say a bit about that.
Yes, yes, it kind of stayed within the name of the paper and within the talk. I thought it is not really relevant to get the bigger picture. I can go into this, yeah. So basically the pret LL star is there because we use, for our internals, we use the xtext and xtend, if you know this framework. And they have this answer parser underneath, which is LL star. And we used the predicates to track our names of the models. So we have this top-down parsing, and when we encounter a model, we saved just simply this name into a table, and then it continues top-down parsing, and when this name is used, then just a very small predicate is checked here if this name already occurred in this scoping. Yeah. Yeah, but that's an interesting question, because we had it once without just LLK parsable, and to be like the step between those two are very small. To make it LLK parsable, you would just have to give it like type hints. You would just have to say, okay, this what you encounter now is, for example, a binary operator, but then you shift the problem into the expansion. So then you have like this LLK parsable language, but then in your expansion you can encounter this symbol clashes or something like this. So yeah.
Yeah, maybe one more quick one.
Just a very quick one. So accidental name capture has always been a problem with macro systems, and I was wondering, when you render your macro system higher order, do you exacerbate the problem, or do you have particular provisions against it?
Yeah, that's also an excellent question, because we were thinking about making it hygienic, but we decided against it because there's just two reasons. The first reason is that we actually want to capture names. So when we generate, for example, this instruction, I want to this X before the operator. It means a register definition that is somewhere done somewhere else before it or below it, like in this, the order doesn't matter here. And we want to capture this X. So this is the first thing. And the second thing, for every new identifier, we do not need an generate random identifier, because we sometimes want to use the name again somewhere else. So we wanted full control over this name. And also in the generated artifacts, it makes it much more readable when you have full control over your name and you just append like a postfix, as we did in the example here.
But you do have a gensim or somewhere as well, if needed.
It's not implemented, but of course you can extend it, yes.
All right, thank you very much.